Please welcome to the stage, Elvis Collado.
Welcome. All right, so before I get started here, I'm just going to run off this, let's check the IP address of this virtual machine here, and then we're going to do an MSF console, ARM, BlueHat, 160, 160. All right, so I'm going to start the exploit before I even start talking, since the exploit takes a little bit. So let's just wait for Metasploit to come up here. So I got tmux and I got screen out the bottom. Let's do all the things. Let's get this going. So once this starts actually spraying the heap, we'll start talking. All right. All right, cool. So welcome everyone. What's up, BlueHat? Black Owl here, and this is your daily reminders. Don't forget to subscribe, hit that like button, hit that notification bell. So anyways, so today we'll be talking about this GreenWave device. It's the G1100. It's distributed by a few ISPs. One may or may not be Frontier, and the other one may or not be Verizon. So there's the FCC ID at the very bottom of it. So what do we do when we have an FCC ID? We go online, we look at everything, and 1 second before I go, I gotta hit this. All right. So we find the internal photos in the FCC's IDs, or FCC's website. We look at the processor here, it's called a Cortina. We have these two memory modules. And then if you're looking, hey, what's this over here? What's this going on, right? This looks kind of out of the ordinary. And if that kind of question popped in your head, you are absolutely correct, because this may or may not be JTAG. So this is 3.3 logic, so we grab our Arduino Nano or we grab our JTAGular, whatever is closer, and then we bit bang around and we find the interface pins. And then also when we open up the box, we have 4 header pins that are already pre-soldered in the middle of the box. As you can guess, this may or may not be UART, surprise. But as we turn on the box, we don't have standard in, we just have standard out, so we don't have any shell when we turn on the box at all. That's sad, that sucks. So I need to get inside this device because the firmware is not public or anything else like that. So I need to grab the firmware first before I even do anything. So we kind of sit back and start thinking about it. I'm like, well, I have that JTAG interface already bit banged. So we put on some header pins. We find a place without much copper at all, get some hot glue, and just put on some header pins and just solder some wires so we can gracefully put on some wires to it and hook it up to our target board. This board right here is just an FTDI based breakout board. It's an FTDI 2232H. So we open OpenOCD with our board configuration, and we get an identifier. Oh, awesome, JTAG. So we see that this is an ARM-based processor, and so either we can look inside the configuration files for the targets to see if we have an ID like ours, or we look at the documentation and just say, let's just create a little NDN Cortex-A based processor as our target. So this is the target configuration. I'm just saying that system reset is a push-pull. We both have test reset and system reset. This is the ID, and then we have a Cortex-A little NDN processor. So then we go back to OpenOCD, we give it our board configuration and our target configuration, and awesome, we have breakpoints, we're in supervisor mode. This is amazing. So all I did here was that I started dumping memory regions from 800 and just kept dumping and piping it to XXD. And what I was trying to look for was the kernel boot parameters. So after a while, I found it, and it just set a watch point to when the very last character is being written to memory. And all I did was just have it stop, and I just overwrote the init. So instead of going to initRD, I just have it go to binsh, which is shown right here and right over there. So after we write, we make sure it's in there, and then we hit continue, and we finally have a shell. This is awesome. So cool. So we have a shell. This is just step 1. So we are now we're able to root the device. So we go through all the init scripts. We bring up everything, and we will come back to this towards the end of it. But out of all these services I looked through, these were actually the last ones I looked at. Like if everyone ever knows, UDP 1900 multicast, SSDP is part of UPnP. Like it's been said a lot of times. So we have 3 different binaries here that are dealing with UPnP. We have this WPS monitor, Frontier 4, and MIDI UPnP-D. But for this talk, we're just going to focus on WPS monitor. So before I even look at the binary, start disassembling stuff, I'm like, oh, I'm going to find a bug in it. I need to know my environment. Like, am I dealing with ASLR and stuff? But very first thing I see is that this could be the UPnP library, the thing that says libupnp. I don't know, maybe it's mislabeled. But I also see that we have ASLR and all the imported libraries. And then also the stack and the heap, we have DEP enabled, so they're not executable. And also as well, the heap is impacted by ASLR, so every time the process is killed and restarted, or the box reboots, the base address for the heap is going to change every single time. So, okay, cool. And then the very last thing is that the main binary is not compiled with Pi, so it's not impacted by ASLR. But if we have a string-based buffer overflow, we have null bytes in the base address of this. Even though it's little endian, we're just only going to have one shot if we do have like something like on the stack or something that influenced some sort of like a function pointer. So we have to be mindful of that. So after that, I just stick in a little USB device into this device here and start just DD everything out of the firmware into a little binary file. Then after that, we open up binwalk and we extract it. Nothing new and fancy. So after this, it's the vuln hunting part. And this vuln, you're gonna laugh. Like, this is silly the way I found it. So I have this crazy, like, very advanced technique where I open up strings and I look for a %s. It's pretty intense, I know. So the very first thing I looked at, so this is about 2 years ago. So the very first thing I looked at was these HP 200 OK responses. And this one caught my eye because there's a %s here, a %s over here, a %s over here, one there, and just one more for good luck. So this thing has %s all over the place. So I'm like, this is pretty interesting. So I looked as to where is this being used, and lo and behold, yes, we do have a sprintf, but the destination buffer is something out of a structure, some sort of member that's being referenced. I don't know if this is the last member out of a structure where it's like a buffer array, and they do like a Stirling on the input, and they calculate it at the end, and maybe this is dynamic or static. I don't know yet. I don't know if this member is dynamic or static yet. So after this, I started looking at the UPnP architecture PDF. You can go on the website at the very bottom there, you can look at the PDF, and this is what all the developers are looking at when they're implementing UPnP, right? So I saw the response where all the %s everywhere, and so I'm like, all right, we have this like, subscription identifier, we have this timeout with the duration, but what causes response? So we keep looking at it, and we see this subscribe method. Now the talk title's coming together. Anyways, so we have this subscribe method, we have the publisher path, which I will tell you guys about in the next slide. Host and user agent are completely optional. We have a callback header that has to be set to a URL, so it's in angle brackets, so like http :/ some IP or FQDN : some port number / the rest of the URI and the angle bracket. And then we have an NT header that has to be set to UPnP event, and then we have this timeout header, which is set to second dash and then some sort of integer. And this is going to be set in seconds. So you can subscribe and be like, I want to be subscribed for 10 seconds, second dash 10. So the publisher path, so we look at all this stuff. If you've ever seen a UPnP talk, it's like, yeah, send an msearch request, and you get this XML back. And we see all these different things, but at the very bottom, we see this, this event sub-URL. And this is what's known as GINA. It's the General Event Notification Architecture. It's right below where you do all these SOAP calls and stuff, right below the control. So anyway, so I learned about, like, all right, so I can trigger this response back by sending a subscribe request, and it's all %s, and I saw that timeout thing, which is something I provide. So let's just bring up our favorite text editor. It could be VS Code, it could be Vim, it could be Emacs, it could be Echo for all I care. Who cares, right? So just create a script in Python where all I'm doing is setting the timeout to a string, and I'm just going to send it, and I'm just going to see what comes back to me. So I sent it, and awesome, we get a %s back, we get our string. Cool, so this looks interesting to at least dive into. I haven't proved anything yet that this is a vulnerability or anything else like that. So I have two things that I can choose from. So I'm kind of crunched on time, and I want to make sure that I'm not rabbit holing. I could spend all the time and do the CSI enhancing, and looking at IDA and find all the members inside the structure and figure out everything by hand. Or I can also, I have it in runtime, so I can just kind of black box it. There's not many states that I can get this server in. You know, I did kind of start looking at all the members and seeing where they're being passed to for different libc functions and you know, just take that type and then be like, all right, this is a character array, this is an integer, this is a short. Or also we can look at like assert statements or symbol functions or simple names for functions. And maybe we find a GitHub where it has this structure defined. And one second. And it has, you know, the rest of the structure defined, and it has these max header lang and max buff lang, you know, pound defined it somewhere. But I didn't have that at the time. So at the time, I just said, you know what, let's just black box it. I already have the device, I have the binary, so let's do this. Kobe. All right, next. So I decided to make a Python script that would just send a request, and if you got a request back, increase the size of that timeout header, and just keep going until you get like a reset or the socket goes down, right? So I did that, and I had GDB attached, and I get this segmentation fault. Ooh, right? But then I look at it, and I'm like, we're loading and comparing and compare to null. And I'm like, this is boring. This is just a loop looking for a null or until R2 and R1 are the same value. I'm like, this sucks. I don't want this. So I decided to play around a little bit more in this. And I'm like, well, let's go back to the manual, right? Like, let's see what else we can do with this Gina stack. So I know there's a lot of words here, but TLDR on this is that you can send a subscription, you get your identifier back, and then if you want to update your duration, you can do that. So if you say like, oh, I originally subscribed for 60 seconds, but now I want to be there for 200 seconds, or screw that, I want to be there for 10 seconds, you can do that. So the way you do that is that you send a subscribe with your SID, your identifier that you got from this first subscription, and then the new timeout duration that you want to do. So go back to my Python script. I have it first send out a subscription, grab the SID, and then just keep updating the timeout over and over again. Got GDB attached. I got a new seg fault. Ooh. So I look at this one. Like, I was expecting it's another load, nothing interesting. And so I look at it, and I'm like, hey, this is actually kind of cool. So what's the value of R3? So I look at R3, and there's my name. Oh, my God. So I am one pointer away now from getting PC control. I got super lucky with this, but screw it. This is my luck. I'm going to count it. So awesome. So I can kind of get PC control, but I'm still one pointer away. I still can't use WPS monitor as a gadget because I'm still bounded by the limitations of a string. And then this has null bytes in it, so I can't use it. And we also don't have an info leak or some way to read out of bounds or get an uninitialized like heap variable or whatever. So I don't have any way to leak any like libc functions or anything else that's being imported. So okay, so let's get into the exploit development part of this because it's going to be fun. So I started thinking about this. I'm like, we're one pointer away. I have one binary that I can use as a gadget. You know what this reminds me of? This reminds me of like Internet Explorer 9 or 10 exploitation where you're like, I have an ActiveX module that I can instantiate and it's not affected by ASLR and I can spray the heap and I can set my fake V table here and bada bing, bada boom, stack pivot over here and we win. So I'm like, okay, so new approach. I need to find primitives that I can spray the heap with. I need to do some David Blaine magic, and then from there maybe I can trigger the overflow and possibly get code exec. So the very first things I started thinking about was like, well, I need a sample of like this base address of the heap because you know it's going over and over. It changes every single time it's loaded up. So I ran it once, got the base address, and I did it again and 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 again. Did it a few times. So after I had like my good pool of like the base address of to where the heap is being loaded, I'm like, okay, how much memory do we have free? And we have about like 117 megs, but I don't want to be too like greedy with my memory, so we'll just call it 100. So theoretically, if the heap always loaded at 0, we could grow it to 06, 06, 06, 06. We have the space available. So awesome. So after looking at my set of like heap addresses, I was like, well, this heap never loads above 03. It did load a few times at 0202, but it was rare, but the max never went to this 03 region. So I'm like, okay, so now I have like kind of a plan of attack. I'm like, I kind of want to grow the heap now. I have this minimum where, you know, I need to get 03s. So let's start looking. So the very first thing I started looking was all the mallocs, all the callocs, all the stir dupes, anything that uses a heap-based function, right? So I find this. So this variable that I called up top, callback stir, it's exactly that. So the callback string that I provide to it after the HTTP, after the port number, or after the IP, sorry, and then the port number, this starting at the slash all the way at the end where the angle bracket ends it, excluding that because that gets null terminated before this. So we're going to do a stir laying on the callback URI, and then we're going to add it to some structure size and then calloc it, and which is going to mem set it to everything to 0, so non-initialized stuff here. But this looks interesting to me. So I set some breakpoints in GDB where I'm like, all right, I'm going to get the length that I supplied to it, and I want to see the return address. So I send it, and I'm like, let's just subscribe over and over again. And they get the same address over and like, what? What the hell is going on? And I like started thinking about it. I'm like, well, if to be honest, like, why would I put 2 allocations for the same subscription? Like, if it's the same port number, same IP, same callback URI, why would I create another allocation? So I'm like, well, let me change something. So let me change the port number. Like, we're doing this for loop, and I'll just have the irritable be the port number. So every time it loops over, it increments, and we'll just do that. So I started doing that, and I'm like, oh, awesome. We are starting to actually grow the heap now by 4K chunks. And then we keep it going, and it keeps growing and growing and growing. So now I'm able to subscribe, increase the port number, subscribe, increase the port number, and go. So I'm filling up the heap. This is awesome. So I found a primitive to just grow the heap. Nothing cool yet, but it's one primitive. So now I'm thinking, like, all right, I can grow the heap now. I'm still bounded by the limitations of a string because we have that stir laying. It's all string-based. So I still need to do some David Blaine Street Magic crap. And then, so I started looking around, I'm like, all right, so I can subscribe and fill up all this stuff. Like, that's nothing. Like, what else can I do with this Geno stuff? And we have this unsubscribe method where it sounds exactly what it is. I don't want to be subscribed to this service anymore. I don't care about any updates. I don't care about anything. Get me the hell out of here. So I'm like, I wonder what this does. And if you're thinking it probably frees the block, you may or may not be correct. So I see where it's being like, there's a pointer being passed to free for this delete subscriber function. So again, back to GDB, I set a breakpoint. And then I just submit a bunch of requests of like subscription. I save the SIDs for every single one, reverse the array, and now I'm unsubscribing. And now we can see that, yes, my 4K chunks that I'm spraying are being freed. So I'm like, okay, cool. We're still bounded by the limitations of a string. So I actually pulled in a colleague of mine who does exploitation for other stuff. He doesn't do embedded, but it doesn't really matter. So I'm showing him, like, this is all my primitives that I have. I can allocate at will. I can make holes at will. But I still need a way to get around bad character restrictions. So he's looking at my notes, like on my, my IDA DB and stuff. And so at the same time, I'm looking at the SOAP interface. I'm like, whoa, there's other layers to this besides the Geno stack. So I'm looking at SOAP, and at the same time, he comes to me, he's like, hey, I found a function that is using malloc, and it's talking about base64 decoding. He goes, do you know where that could be used by? So it kind of struck me. I was like, well, let me look at the SOAP actions, and I found this one where there's no out arguments, only one in. Beautiful. And this AP settings, we look at the very bottom of the XML. We find the type. It's a base64 encoded string they provided for the type. I'm like, huh. So I send out this base64 like encoded string, and we find out that the allocation that it gets, it will copy the base64 string into it and then decode it into that same block, and then once the TCP connection is killed, it frees everything. So I'm like, okay, it's a new plan of attack. I unsubscribe, I do my base64 encoding stuff, it gets freed. I now put another thing at the top of the free list for that 4K chunk and keep going and going and going. I'm like, awesome. And then if I look inside this chunk, you can see, like, yes, there's my first gadgets right there, but you see the O2s, you see the O3s, the O5s, O6, O7s. That was just me playing around when I was working on this to get everything aligned properly to see how reliable could I get this. And it's pretty good. But either way, I now can send a base64 encoded string that gets base64 decoded into the heap, so now I don't have any more bad character restrictions. So, to go back, I can spray the heap now. I can kind of do some magic, but there could be some races that may happen, and we'll discuss that. So the very first thing I noticed was this. So I did my spray, I'm allocating everything, and I'm like, unsubscribe, base64, I'm doing this, everything's going great. And I'm like, all right, let's check out the address I want to look at. And I see this, like memory address cannot be accessed. And I'm like, what the hell? Like, what's going on? And I started thinking about it, and I'm like, well, you can't really build a house without a roof. So instead of doing this where I'm allocating everything and I do a free and I do a base64 encoded request for that SOAP action, and I keep going down, keep going down. So eventually as I keep going down, hold on, all of this is free. So this is all unallocated space now, it's all free space. So the Linux kernel is going to come in, and it's going to claim back the memory it just allocated me. So now I have this race where I have to race, before Linux takes back this memory space. But that's not good, because I'm doing this all over a socket. There's no guarantee that I'll be able to beat the Linux kernel before it reclaims that memory. That's stupid. So instead, I do all these subscriptions, and I leave the last subscription in place. So that's going to always be there, because one of the things that you can provide for the second parameter is infinite. So instead of specifying some huge integer, you're going to say infinite, and that subscription will always stay there until the device gets rebooted. So now I go second to last and start doing the same thing now. And everything is working great. Now the heap no longer gets pulled back, and now I have like a roof to this, to this house, you can say. But the other thing I started noticing was that the base64 decode function was picking up the same thing over and over again, like it would just happen halfway through. So okay, so now I have to troubleshoot this. So now I'm going to set a breakpoint at free and see like what exactly is going on here. So I attach some devices and trying to do like real world traffic and stuff. So I see this. The very first thing I see is that the SSDP process function is getting hit. So anytime it gets a message over multicast 1900, like an msearch, a notify request, it's going to allocate stuff to the heap. And also, if the device requests, like does an msearch request, it gets the 200 OK back, gets the XML, and then it requests it over HTTP, that's also going to allocate something to the heap. So what I did first was that I create two pools. So I create one pool where these allocations, where they're pretty small in size, can go into this area. So I do a bunch of subscriptions and I create holes into it. And then after that, I create my next pool, which is this thing. And then as well, I can't do anything about the TCP race. But what I can do is try to spam the top of the free list over and over again to make sure I'm always there. So what I do now is I free and replace 5 blocks. I resubscribe again to go back up, and I go back down again, and then iterate to the next 5, which increased the amount of time the exploit takes to run, but it increased reliability by quite a bit. So now I can spray the heap. I can do some magic without like picking up pointers that I'm not expecting or anything else like that. Like this technique that I just kind of did over and over again and fine-tune it is starting to work out pretty well. But I need to dev out this exploit chain. So I started thinking, I'm like, let's just run the crash. Like, let's just get a crash and see where we're started. Out of all these things, I do control R3, which is a value, but the only thing I control for the insides of it is this pointer for R4. So inside R4, we see our attack string. So the 42s, it's just, a bunch of Bs. So this was 2 years ago, it's putting in the mindset. So I used to do like IPS filter development, so I'm really good at PCRE regex, even though this is the worst regex known to man. But all I'm looking for here is that I'm looking for a load where R4 is being dereferenced. I don't want any offsets right now, just give me everything for that and I'll do the offsets later. So I got a bunch of results, And I went one by one by one by one by one, and this is how I found all my gadgets. I just did it all by hand. Like, I didn't use Ropper, I didn't use any of these automation ROP tools. I tried to use one for a stack pivot, but we'll look at that in a minute. So just to go for a high level for this call stack I'm going to talk about. So gadget 1 that I found grants me the ability to call a function with 2 arguments. That's all that it does. Gadget 2 allows me to do a stack pivot, kind of. It's cheap. But then we get control of R4 to R7. R7 is going to have a pointer for the IAT table entry for string to unsigned long, -4, because that's going to be dereferenced +4 later on. We'll store that into R0 and get control from R3 to R7. And then from there, we deref R0 +4 into R0. So now R0 is pointed into libc at stir to unsigned long, get control of R3 to R7, and we add R3 and R0 and store result in R0. So now all I'm doing is taking where we have our pointer that's inside libc as string to unsigned long, and we're now adding an offset to it, so now I'm pointing to popen. And then we get control of R4. R6 is going to store the value that I just calculated to popen back into the heap, since we don't really care about it anymore. The heap is not this fragile state thing that if something overwrites it, I get worried. We can do whatever we want at this state. And gadget 7 is just gadget 1 again, because all I'm going to do is pick up that pointer that I saved to the heap, and I can call it with the command to execute and the argument R. So gadget 1 looks exactly like this. So R4 is our attack string, and we deref that and put it in R3. R3 is now going to be a pointer that's going to be calculated to get R0 and R1. I'm doing 4K chunks, so all at the end of it is just going to be like 40 and 20, and then 10, 14, and C. So like, it's not going to, it's controllable. So this one actually worked pretty well. But the problem is, this is a heap overflow where I can call in one function. Like, I don't have control of the call stack yet. This is not a stack-based buffer overflow. So I had to think about this. So I went online, and I started looking up different research for like stack pivoting on ARM, and I found this old 2012 slide about this thumb instruction called load multiple decrement before. And so I decided to try it out. So I loaded up Redare and started looking up this load multiple decrement before with R4 as the source, plugged it in, illegal instruction. So this is not going to work. And I was like, why isn't this working? And so one of my colleagues pulled up the ARM manual and was like, well, the restriction for this instruction is that the reg list cannot contain SP. Okay, so I can't use this instruction to stack pivot anymore. It's part of the restrictions. Okay, so I'm like, well, what else can I use in order to like stack pivot? I'm like, well, instead of trying to get the stack pointer to point into the heap, why don't I just bring the heap to the stack? So I started looking at mem copies. I started looking at every single one by one by one by one, and I came across this one, where R1 goes to the R4, R0 goes to R5. Long story short, I can provide the end parameter, the size, and the source, and the destination is the second to last instruction there, which is a stack-based pointer. So I can use this, where I provide a source address, the size of it, and it's going to smash the hell out of this stack. The only problem is once this returns, this is a large stack frame. So I'm starting to run towards the edge of this stack here. So if I keep going with my call stack, I have to be careful not to run out of space, and then that's the end of it. So everything again. So all I'm doing here is like I got this pointer to string to unsigned long from the IAT table, and I'm just dereffing it, and then I'm calculating off the popen, and then I'm saving it to the heap, and then I'm calling it. So to put it all together. So we're going to spray the heap. We're going to save all the description identifiers. We're not going to free the last description identifier. That's going to be our root for the heap, so the OS doesn't reclaim that memory. We're going to free and replace the blocks via the unsubscribe method and also to invoke that SOAP action. And we just basically forward encode our fake struct, our ROP chain, and the command that we're going to execute. And then with also the idea of that we're going to free 5, reoccupy 5, free them again, and go on to the next 5. And also listening on multicast traffic, so I have a multicast UDP listener, and I just select it. If any data needs to be read, we read it all, and then we occupy 25, free them, and then return. So then we trigger the vuln. So hopefully we can always stay on top of the free list, and nothing else can race in and screw it all up. So we do everything, and this exploit is still running, so that's okay. So we may win, so we run everything, and after a while, after this one says 24.78 minutes, this one is still running. We do get a shell, and this is awesome. So the last things I want to talk about, though, all right, that's still running. So the bonus material. So going back to the services that are on this device. So this particular one, when I first looked at it, pointed like right out to me. NVRAMD, and it's on port 5152. It's listening on all interfaces. So I'm like, great, this sounds interesting. Maybe I can change some NVRAM parameters or something. Try to connect to it, not working. Look at IP tables, it's being blocked, so I can't reach it from an outside source. So I started thinking about it. I'm like, well, what about the callback thing? What if I set the callback to 127.0.0.1 and I set the port at 5152, which is that TCP listener port, and maybe it's going to send a notify slash or space slash this string I sent. So we attach strace to that particular daemon. We send this subscription request to the UPnP service, and we see it. We see that it does connect to it locally, and we can send stuff. So if this was like a token-based service where it's like I'm looking for a subcharacter or substring, and they go from there, this could be a great way to pivot. Unfortunately, for this particular service, that wasn't going to work because it also looked at the very beginning of the stream, which I don't control, notify space slash. I don't control that. So all right, so I'm going to stop this here, and this exploit didn't work. That's okay. All right. The one thing, though, that I want to show you, though, was that, man, I can't believe it didn't work. Anyways, doing all this by hand took a while. And so I started to learn that I should start doing like automation to start looking for these kind of stuff. So I started creating a test case suite for all this. And let me show you that. So finding the vuln for this did take me a little bit just because it was the last thing I looked at. But creating a test case suite for everything made it so I can set up like a script that will find the common type of things that I find in almost every single UPnP library or I have found. Or I can look at the documentation and think of new ways in order to see if I can make something go down. So let's see. Man, I can't believe that didn't work, but that's fine. So we're just going to start everything up. And this thing takes about a minute to boot up. So the very thing at the bottom screen here is just the screen session for the UART interface. Man, can't believe it didn't work. Oh well. So it's setting up everything. It's booting up everything. Man, 20.95 didn't work. I like how this exploit, I've tried it 1,000 times and it's worked, and I try it here live, and no, it doesn't work, but that's okay. We'll do the next thing. So what I started doing here is I was thinking about it, and I'm like, well, I want to create a script to start testing for all these type of things, but I don't want to make like a GDB server stub or anything else like that. So I started thinking about when I used to do network engineering. And so when you set up like a local load balancer, the one thing you're doing for your server farm with every single real server is that you have to set up a health check, like a layer 4 health check or a layer 7. Like I'm going to probe this socket, and if it's healthy, I'm going to close it and call it up, or I'm going to do a GET request for this web page, and I'm going to expect like a particular string or something before I call it OK. So I'm like, well, why can't I do that with UPnP? So the whole basis of this program is it's really, really simple. So we just send out msearch requests. Let's see here. Whoops. So all we do here is that we send out these msearch requests, and we discover all the things that are within the network, like all these different UPnP services. And so all I have here is that once we discover everything, we're going to start fuzzing everything as well. For this particular demo and such, I have all the SOAP action test cases turned off and just my Gina ones turned on. And once it finds something, it's just start playing a sound. So this one right here is going to start fuzzing the MIDI UPnP daemon, and it's going to be fuzzing the Gina part. It's going to find one bug that I already published in my GitHub. It is fixed upstream, but it's a read out of bounds. Due to them using smprintf to limit the copy, but they use the return value from smprintf as a value for the end parameter when sending the notify. So smprintf is going to return a much larger value, and then it's going to read out of bounds. That was loud. So we have an info leak. So that's MIDI UPnP right there. So we're just going to keep waiting. There are 3 UPnP services on this device. And so it's going. So let's see, come on. So it should just be a little bit longer, and then, all right, so here we go. So let's get rid of that one. So this one, 19900, is going to be the WPS monitor one. So we have the read out of bounds from the previous service, as you heard. And then this one right now, so I have like, so we have another POC that gets written. And then after the end of this,
son, where'd you find this?
we have our POCs being generated. And so what this script does is that, so if we look at the 192 one, this is going to be exactly what I found statically. We have this header where the timeout is being set to second dash, and this is probably really hard to see. And let me see if I can increase this a little bit. It just says test case 11, TC11 over and over again. And so this particular script that got generated, I can just run it again with GDB attached, and it should present me with a crash, and I can analyze it as well. We can also look at the other one that got generated. Let's see here. So this one right here, if it looks a little weird. So anyways, this one right here was MIDI UPnP-D. It was impacted for a little while, like devices such as Google Wi-Fi, Samsung router thing, I forgot the name of it, and a few others that use MIDI UPnP-D were affected by this. So the root cause of this was that it would allocate a 1024 byte chunk for the response to be sent back, and it used smprintf in order to limit the copy, but it used the return value of smprintf for the end parameter for sending back, so you could read out of bounds. So what you could do is use the subscriptions to also make a hole somewhere, so when you're about to read out of bounds, you can read into structures that you know are going to be there, or at least it's going to have a high chance of landing to an area that you just created with the subscribe and unsubscribe methods. So this is, I thought about releasing this tool and such, but at the end of the day, it's just an XML parser and an HTTP-like thing. Like, this is a great tool, like great exercise for anyone to try if you're interested in like kind of like router stuff. If you want to make something that's gonna like test your, like, just do something that you see over and over again, this is a great way to do it. It's where you just send a request and then you check to make sure the socket is up. If it's not, then you take the last request that you just sent to memory and you generate like a file, or you just save what you sent. So doing this saved me so much more time. So to wrap it all up, so to wrap everything up, so this is my last thing. So that was the fuzzing demo. So all it did was just like kind of showing to me like, well, you know, if I spend some time automating some of the stuff I do by hand, it can increase my workflow, and I can actually do both side by side, where I run a bunch of test cases and then I also do it statically just to increase my workflow time. So this is the end of it. This is who I am now. So I'm Black Owl. I'm a zero-day researcher at Exodus Intelligence. I do embedded devices, Soho, smart devices, whatever. So this is my talk for BlueHat. That was, again, don't forget to subscribe, hit that like button, hit that notification bell, and until next time, I'll see you guys. Have a good night.